right?
If we
So that,
draw the Fisher projection with OH on the right side,
yeah, better to draw the molecule. So you said it's 5 carbons and it's a Fisher projection. How many stereo centers?
sir, that is the question. First, can I tell the molecule?
You mean in the class test?
No, sir.
Previous class?
Yes, sir.
Uh-huh.
Sir, CH2OH on both sides, like two COOH groups. Sorry, COOH on both sides.
Yes.
And there are total 5 carbons.
5 or 4? Oh, 5. Okay, all right. Yeah, all right. I got it. The pseudo asymmetric center, you mean?
Yes, sir. Sir, on the top one there is OH on the right hand side and H on the left hand side. Bottom one, no sir, OH on the left hand side.
I don't think I have drawn that molecule, but it's fine. That's good to discuss. Yeah, okay. And then middle one?
Middle one can be anything. So sir, I was asking whether the middle center then will be a stereo center or not.
Okay, okay, okay. That's great. That's good that you asked. So let's randomly put OH here and H here, okay? That's fine.
Okay, sir.
So the next job is to determine the absolute configuration here in both cases. Okay. So if you look
Yes.
at the lecture, last lecture, the first job we did was determining the absolute configuration of the top carbon and bottom carbon, and then we analyze the middle one. Okay, so we'll do the same. Let us do that. So what about the upper one?
Sir, I think it will be S.
1, 2, 3, 4. So it's coming, I think, no, R, no? R.
Oh, sorry, sir.
Yeah,
Okay,
no
okay.
problem. That's fine. So this is R. Okay, so what about this? This is number 1, number 2, number 4. So 3 here. So again it was going, and then again coming clockwise. So it's becoming R as well. Okay?
Yes.
So both became R. Okay. So now can someone comment on this? Or you can also. So now what's the fate of this? Both are R. That means both are identical. So this guy is having 2 identical substituents. So it's almost like this. The situation is similar to this. Huh? Is this a chiral center? Middle one?
No, sir.
No, why not? Because this
Sir,
is having two identical substituents, right? Same here. Only difference is here 2 substituents are chiral, 2 groups basically. It's having 2 chiral groups, but both are same, both are R. So in this case also, it's not a chiral center. Okay, so if you recall previous class, it was one was R, one was S. In both the cases, doesn't matter if you put here or here. In both the cases, it was one R, one S. That means these two are not identical. Then we said that the R1 will get higher priority. Then we could assign one absolute configuration, either R or S, but it was a small r or small s, because if we take reflection, it was not giving the absolute configuration was not changing here. Which one is a small r was remaining small r, which one is a small s was remaining small s. That's why I mentioned that this stereo cell is a special one and it's fulfilling partially the characteristic of an asymmetric center. Okay. So partial fulfillment is it's having 4 subsequent which are different, but on reflection it's not inverting the absolute configuration. Okay, only half is maintaining. That's why it's called pseudo asymmetric center. But in this case, it's absolutely a normal asymmetric center. Normal symmetric center. It's not asymmetric. Symmetric because it's having at least 2 identical substituents. Okay, is it clear?
Okay, sir. Thank
Yeah.
you.
Okay.
Sir,
Yes, go ahead.
I have small doubt. So in the previous class, we told that if we are having R and S, then the center carbon we will change a chiral, and we will give the higher priority. So we will take it as R. So small r. Is there any other? Means in which condition we will take it as small s?
Oh, okay, that's good. It's the same, no? If we get by analyzing using our method CIP rule, if we get a absolute configuration becomes S, then it will become small s. Let me do it. Before that, we have to change here. You can the same molecule you can do. Before that, I know we need to change here. OH here, H here. Okay. Then it will become S. In this case, it will become S. Let me directly draw S. Now the situation is R and S. I think this will be like this. We can do it. Yes. This is S, R and S. Okay. Now let us try. This is definitely 1. This is 4. As we said, between R and S, R is high priority, so this is 2, this is 3. Okay? So it is going clockwise, but because least priority is on the horizontal, become anti-clockwise. Okay. So final rotation is anti-clockwise, so it's becoming S, but as we know, this is
Okay, sir, got it.
yeah, this is small s. Okay, I think things are clear now. So with this, we'll start a new topic. And by the way, this is the last class on stereochemistry. It's the 8th lecture. From next class onwards, we'll start diaromaticity. In today's class, the thing we'll discuss is a bit different from the previous classes. So as you know, this is the lecture on chirality or asymmetry. And then from the first day itself, we started our discussion on asymmetric things. So all this asymmetry and how to draw molecule, how to assign the configuration of the asymmetric center, blah, blah, blah. But in today's class, in contrast, we will discuss on symmetry. Okay. So on the molecular symmetry. And this is important, although it's a contrast to asymmetry. Someone can ask that in an asymmetric course, why should we learn on symmetry? But you know, if there is no dark, there is no value of light. So like that, so here, unless you learn about symmetry of a molecule, you will not realize the asymmetry of a molecule. That's why it's important. And later on, you will see that it's very helpful, basically, and important knowledge to analyze the molecule or molecular symmetry, rather. Okay. So there are actually 4 kind of symmetry elements. By the way, there is a whole topic on molecular symmetry. The group theory is there, the whole theory is there, and there are a lot of mathematics involved there. Maybe in some other course you will learn that. In this particular course, we don't have that much time. So what we learn here, only the gist or the important aspects from there we'll take, and we'll learn that is that we need to apply on chiral molecules. So if you are interested, you have to go back and learn about group theory. I'm sure you will learn it in some other course, but only the required thing we will learn today in a brief fashion. and we'll apply on chiral molecules and we'll see how these are helpful. Okay. And in these symmetry elements, so the topic is symmetry elements or molecular symmetry. There are 4 symmetry elements are there. Yeah, there are 4 symmetry elements. So let me first write those 4, and then one by one we'll discuss with the help of molecules. All right. The number 1 is, let me make a table, then it would be probably easier. Let me like symmetry element is this symbol, maybe the operation. I'll explain everything. What are these? Okay. Number 1 here is in the first symmetry element. AC is the symmetry element. Axis of symmetry. The symbol is Cn, and the operation is rotation. Someone can ask, what is this operation thing? Operation is whenever, suppose you are given a molecule, and then you are asked that please identify the symmetry element present in this molecule, if any. So then you have to perform certain operations, okay, like rotation, reflection, inversion, this kind of different operation. I will tell you, show you how to do that. Only after performing these operations, you will come to know whether this molecule is having a particular symmetry element or not. Okay, yeah. Yeah, Cn. Yes, Cn. Yeah. All right. Whether after performing this operation, you will come to know whether that molecule is having this particular symmetry element or not. Okay. So with the real molecules, we will also see in a minute. So this is first let us write these things. So axis of symmetry is represented by Cn, and the operation is rotation. Next is plane of symmetry. Plane of symmetry, and the symbol is sigma. Okay. And the operation is reflection. Number 3, point of symmetry. Point of symmetry. Here the symbol is I, but some people also write Ci. So both are okay. Some people write only I, some people write Ci, both are okay. Here the operation is inversion. The last one is alternating axis of symmetry. Alternating axis of symmetry. The symbol is Sn. Sn, yeah, like teen, but N is in superscript, subscript. And here, this particular symmetry element has a pair of operations. Okay, so we have to perform 2 operations to verify whether a molecule is having Sn or not. That is rotation and reflection. Okay. Rotation, reflection. Both you have to perform, rotation and reflection. You will see with molecules, as I'm saying. Okay. So these are 4: Cn, sigma, I, and Sn. Okay. And so as I said, these are symmetry elements. Okay. The thing is, whenever Someone can ask you, so what's the utility or the usefulness? So with this, there are so many, of course, so many utility and usefulness or application of this. But one quick one I can say, just suppose there was a molecule given to you, and then someone asked whether, tell me whether this molecule is chiral or not. So the actual way is to take the molecule and take a mirror and then get a reflection, and then from the reflection to make another molecule and then superimpose these both, right? But it's not feasible every time. It's a really, it's a long job. The shortcut way is these symmetry elements. You just take the molecule, perform certain, draw in a paper, and then perform certain symmetry operations and check whether these molecules are having any symmetry element. And if yes, then you can say, yes, this molecule is having symmetry elements. That means this is symmetric. That means as a whole, it's not, or other words, it's not asymmetric, so it's not chiral. Okay. So like that, you can comment easily, very easily. You can comment on the chirality of a molecule just by performing the symmetry elements. Okay. So this is just a small utility. There are many more. But one thing I should mention at the beginning itself, although I've mentioned 4 symmetry elements, but the application, as I said, that whether if a molecule is having a symmetry element, then that molecule becomes symmetric and it will not be chiral. But that is only limited to, or absolute or limited to these 3. Okay. So I'm telling again, if a molecule need to be chiral, or a molecule becomes achiral, sorry, not chiral, achiral, because we are discussing on symmetry. If a molecules need to become achiral or symmetric, then that molecule must have either sigma or I or Sn. Okay. This Cn, although it's an axis of symmetry, but this axis of symmetry cannot decide or cannot decide the fate or cannot decide the property of the molecule, whether it's chiral or not. Okay. So that in other words, if a molecule is having Cn, we cannot comment that whether this molecule is chiral or not. So if it's having Cn, only Cn, that molecule can be chiral. Okay. But if a molecule having sigma or I or Sn, then only we can say this molecule is not chiral. This molecule is symmetric. Okay. So this is the thing. Please keep in mind. Axis of symmetry cannot decide the chirality of the molecule. Okay. All right. So after this, let us discuss in more details one by one with the example of the real molecules. So we'll start with Cn. This Cn is nothing but the rotation. Okay. What is that? 360 by n degree rotation. Okay. Let us take one molecule. So that's the best way to explain. Let's take this molecule. ClH3. Okay, so you can already see this is nothing but methyl chloride. Okay. Let me take this and model. Okay. Let's take this one. I don't have the green today. Normally you take chlorine as green, but doesn't matter. Let us consider this red is chlorine today. This is this methyl chloride here we have. The thing is, if someone asks, give you this molecule and then ask whether this molecule is having the axis of symmetry, what you have to do, you have to find out one axis. Right? You have to find out one axis, and then you have to rotate the molecule around that axis. Okay? You have to rotate the molecule around that axis. And the second thing is, suppose you have to fix one initial point. Suppose you have, this is the initial point, okay? This is the initial point. And then let's suppose this is the axis here, going towards from here and going through this carbon-chlorine bond here. And next job is, you have to find out that the axis is done, the initial position is also done. Now you have to rotate, the operation is rotation. You have to rotate to certain degree so that the molecule regains the initial position. Okay. So I repeat. So you see, this is the initial position where the carbon chlorine is like this, one hydrogen is going like this, and another hydrogen is towards you, and the last hydrogen is away from you. Okay? And you have to rotate the molecule to a certain degree that it regains the initial position. You see, again, initially, again, you see in this position also is the same. Carbon chlorine is here, this hydrogen is on this side, one hydrogen towards you, one hydrogen away from you. Again, you do the continue the rotation, you will regain the position. Okay. Now the thing is, what is this amount of rotation, or what's the value of this degree here? Can someone please comment on that? So how much is the required rotation here to regain the initial position? It was the initial position, and we are rotating like this to certain degree and regaining that position. Again we rotating, again regaining, again rotating, regaining.
120
Exactly.
120.
Right, absolutely correct. So the thing is, if you have the axis here, if you rotate it by 120 degree, then you will regain the initial position or the identical position. Okay, so that means in this case this degree is 120. Okay, so after dividing by n, it should get 120. Okay, so then this gives the value of n, what you can easily guess, is 3, right? So in this particular case, n equal to 3. So that means this axis around which we did the rotation, we'll call it C3. Okay, so I repeat the things once more. You have to find out one axis, imaginary axis, and there should be an initial position. Then you have to perform rotation around that axis for certain degree. And if you regain the initial position after performing that rotation, then you have to find out the value of n. Okay, from the degree you can easily, because the right hand side is 120, from there you can see already. In this particular case, n becomes 3. So then we will call this imaginary axis as C3. Okay, so that means this molecule is having one C3 axis of symmetry. More example. What about this guy? Although I have, while drawing it becomes a little bit deformed, but as you know, it's not deformed, all the bonds are same. What about benzene?
Sir,
Yes.
you are asking us to consider the resonating structure or the hybrid structure?
No, the hybrid. I mean, you can't consider as a. Okay.
So then it's 60.
Yeah. That means then you can see only 60-degree rotation, and the axis is how? If we consider the benzene ring on the plane of the board, then axis is going like this, isn't it? Like this is perpendicular to the board. and then you are rotating. If you rotate only 60 degree, this carbon will go there, this carbon will go there, will go there, go there, go there, and you will get an identical structure. Okay, so that means it's only 60 degree rotation this time, and which gives you have C6. Now question is this the only axis of symmetry this molecule is having?
No, sir, even on the plane of the molecule.
Yes.
Yes.
That what
Yes,
the
C2 axis.
C2 axis. How many?
6.
Right. 6 actually. Through the carbon here, you can easily visualize. If you rotate by now, it's 180 degree now. Then it will just, ring will flip, and then you will get another identical structure. So this becomes 180, value is 180, so N becomes 2. This becomes C2 here. Okay. You can do the same here, through these two carbon, through these two carbon. And the things is, not necessarily have to go through the carbon-carbon. In between the carbon-carbon bonds also you can have. You can flip the molecule from here also. Okay, so you just take a square something, if you have, not square, hexagonal something at home, and then you can flip and then try. Everything here, also here, and then here also. So basically, there are 1 C6 plus 6 C2 axes are there. So benzene is a highly symmetric molecule. Okay, so it is having that many axes of symmetry. Okay. What about the other symmetry elements? What about plane of symmetry, the sigma? Yes. Any query? Okay, if not, then we continue. Next is plane, the sigma. Okay, sigma is also very easy. Here, let's take this guy. Okay. Sigma is nothing but you have to find an imaginary plane. Okay, imaginary plane which will chop the molecule into equal halves. And it's not really equal. The thing is, you have to chop the molecule, and imaginary, you have to find out an imaginary plane which will act like a mirror. Okay, act like a mirror, and both part of the mirror should be mirror images of each other. For example, or in easier thinking is, you just chop the molecule into equal halves. At the beginning you think like that, and later on will maybe the mirror thing will come. Then it should be easier. For example, this molecule. Okay, as you can see, this molecule, there is no chiral center, nothing. These are only 4 atoms are there, 6 actually, 2 carbons and 4 substituents. And as you know, all sp2 hybridized carbon here. So that means this molecule is absolutely planar. And you can think that it's on the plane of the board, and you can easily think about an imaginary plane which is on the plane of the board itself, and which will chop the molecule in equal halves, isn't it? So you have this molecule, and then you imagine that there is a plane which is chopping the molecule into equal halves. Okay? That is the nothing but the sigma, the molecular plane, and this is the plane of symmetry. So any planar molecule, which is absolutely planar, it's not like the only some part is planar and you have a chiral group here. That will not be. But these are fluorines are a single atom, right? So you can consider as one sphere here, which can be chopped through the plane of symmetry, which can chop, and then you will get 2 equal halves. So this molecule is having a plane of symmetry, the sigma. Okay? And not necessarily the molecule needs to be planar to have plane of symmetry. We can have drawn this molecule already, that methyl chloride. Okay, methyl chloride is there. Here also we can have plane of symmetry. You can see this is the methyl chloride, right? If I hold it like this, then it's easier. Now think about it. Maybe I'll point it here. That is even easier. Okay. So one hydrogen is towards you. I'll just hold it like this so that you can easily visualize. Just chop the molecule through this carbon chlorine and cut it like this, and through this carbon hydrogen. Okay, the plane is like this. Okay. Yes, exactly. First, you have to chop this here, and it's going through there. Okay. Then what will happen? So you are chopping chlorine carbon, this chlorine carbon hydrogen, and two equal halves. This side hydrogen, this side hydrogen will be identical, right? That's a perfect sigma here. Okay. And not necessarily you have to consider this hydrogen. You can chop the molecule here also, as he said. This carbon chlorine and this hydrogen you consider, then this will be equal halves, and same here you can third carbon hydrogen also. So there are three sigmas here. Okay, this molecule is tetrahedral. That doesn't matter. It not necessarily has to be planar. Still you can have the sigma here, chopping this side or chopping this side. This is also sigma. So this molecule chopping this side also having sigma. So there are three sigmas here. Okay, you can chop each side and then you get sigma. And now the thing is, so we are discussing on sigma. There are two kinds of sigmas are there. Okay, one is called sigma horizontal and one is called sigma vertical. So what is that? To determine which one is the sigma vertical and which one is the sigma horizontal, we need to first find out the axis of symmetry in that particular molecule. Okay, so we have already learned about axis of symmetry. After knowing the axis of symmetry, and with respect to that axis of symmetry, the position of sigma will determine whether we called it as a horizontal plane of symmetry or vertical plane of symmetry. Let us discuss with these examples. First take this one, this molecule, which is trans dichloro, 1,2-dichloro, ethene, right? We have already seen the sigma here. Now tell me, is this molecule having any axis of symmetry? This molecule? Is there any?
Yes, sir.
Where is that?
So it's like coming either out or into the plane of the board.
Yes, exactly. It's like, no, it's like the C6 of benzene here. This is a planar molecule, and isn't it? Like this here. And if you rotate 180 degree, then this chlorine will go there, this chlorine will come here, this hydrogen will go there, this hydrogen will come here, and you will get identical structure. Isn't it? Rotate by 180. That means this molecule is, I'm drawing in 2D, that's why I'm drawing like this, but it's not on the plane of the board. It's like this, okay? Half is from starting from here, bisecting the board, and then it's perpendicular to the board. Okay, and this is C2. Is there any axis on the plane of the molecule board, basically? Is there any on the plane? Is there any on the plane? Okay. What about this? We'll discuss on that, whether it's having on the plane or not. The other brother of this guy, the diastereomer, geometrical diastereomer, cis this time, cis dichloroethene. Previously it was trans, this is cis. Can you please comment on the axis? Axis of symmetry here?
It's on the plane.
On the plane. Is there anything perpendicular?
No, sir.
No. This is the contrast here. You see, in this particular case, it's on the plane. C2, if you on the plane, you rotate like this, then this will flip. This carbon will come here, this carbon will come there, so this chlorine will go there, hydrogen will come here. Everything will get exchanged, and you'll get identical structures. So in this is the difference here. In this particular case, the axis is here on the plane, is a C2, and in this particular case, this is perpendicular to the plane, and this is also C2. Okay. Okay. What about the sigma here? Is this molecule having sigma, plane of symmetry?
Yes, sir.
Yes, sir.
And is exactly the same, isn't it? Because this is also the planar molecule. Doesn't matter whether chlorine is trans or cis. Exactly the plane of the board or the molecular plane is the sigma. So in both cases, if you compare these two, sigma is the same, the molecular plane on the board, but C2 is different. In one case is perpendicular to the axis, and one case is on the plane of the molecule. Yes.
So
Won't there be a sigma crossing the in the
Yes, sir.
between the bonds?
Yes, yes. One case.
Coming out of the board.
In the
Yes.
second,
Yes. Yeah, I'm coming into that. Okay, so I have drawn these two molecules just to compare things. Let me just give me 1 minute, then you can ask. Probably will get the answer already. Okay, so I started the discussion by saying that there are two kinds of this plane of symmetry. One is horizontal, which is designated as sigma h. Okay, and there is another one which is vertical, which is designated as sigma v. So what are these two? Sigma h is nothing but which is perpendicular to the principal axis. Continuing or okay. By the way, I've written one term, principal axis. Let me first clarify what is principal axis. Principal axis is nothing but the molecule, when a molecule is having several CNs, okay, like benzene. Suppose in benzene, this molecule is having several CNs, right? One C6 and there are 6 C2s. Okay. In those cases, when there are multiple CNs, the axis with highest n value will be called as principal axis. So that means in this case you can see already C6 is having the highest n value. This will be called as a principal axis of benzene. Okay. But when the molecule is having only one CN, so then it's a lonely king. So automatically that will be called as principal. Okay. When in case of multiple, then only this n value have to judge. If it's having only one, then that becomes principal itself. Okay, so now you compare. In one case, sigma h is nothing but which is perpendicular to the principal axis, and sigma v is nothing but which is containing the principal axis. If you come back to these examples, the upper one, you see where is the trans. This molecule, by the way, having only one CN. Okay, so it's not like benzene; it's only having one CN. In this particular case, is this going like this, and the molecular sigma is like this. So in this case, this principal axis and sigma are perpendicular. So this case, it will be called as sigma h. Okay, and this particular case, you can see the sigma and is containing the principal axis, so this will be called as sigma v. Okay, it's fine. I think you got your answer. Why this sigma v and sigma h important? Actually, we'll see it later on. But we'll go back to benzene now. Okay, we'll go back to benzene and discuss the sigma here. I've just erased methyl chloride, but please note that you can see already in methyl chloride the C3s are here, right? And the sigma was also there on the same line. Okay, so that means in all three sigmas are containing the principal axis. So in methyl chloride, all three sigma planes are sigma B. There is no sigma H in this methyl chloride. Okay, so as I said, I'll go back to benzene here. Is benzene having any symmetry elements, plane of symmetry?
Yes, sir.
Yes,
It is a
sir.
planar molecule.
Yes, so it's a planar molecule. You can think about a sigma plane on the board. So now tell me, that is sigma H or sigma B?
Sigma H.
Sigma H. So the sigma which is on the plane of the board, that is sigma H. Is the only sigma this benzene is having?
No, sir.
What about other
There's
one?
a sigma V also.
Six
There's six
sigma B
sigma Vs.
also. Six
Yeah,
sigma.
exactly. So there are 6 sigma B's. So exactly same like this, it's chopping, going here, 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 like this, no? 6 times. Okay? And all those sigma B's are containing the C6. You see, C6 is here, and sigma B's are like this. All the sigmas are here. So this molecule is having only one sigma H plus 6 sigma B's. Okay. All right. So that's the thing. Okay, so we'll proceed. This is about symmetry, plane of symmetry. What about point of symmetry?
Sir, in case of the second molecule,
Yes, yes, please.
sir, the second molecule in the board,
Mm-hmm.
sir, we are having one more sigma V, right?
Let me check. You mean this one?
Yes, sir.
This is there. Oh, yes, yes, you are right. You are right. There is another sigma V. Very good point. This is one sigma V is on the plane, right? Another is here, right? Which is out of the plane, which is perpendicular to the board, but containing C2, isn't it?
Yes,
That is
sir.
what you meant, right?
Yes, sir.
Yes, very good that you have realized that. This is like this, okay? So which is perpendicular to the board, but still containing C2, right? So that's why that is also sigma V. Yeah, it's also sigma V. There are two sigma V's
Sir,
here. Yes.
similarly, in case of benzene, along each C6,
Hmm.
there are also a plane of symmetry.
Yes, yes, that is we have mentioned, right? There are 6 sigma V's also, like these. Through 2, 3 between
Sorry,
chopping.
C2. Sorry, sir. C2. Containing C2. Each C2 axis there is a plane of symmetry.
Yeah, there are 6 C2s, right?
Yeah.
There are 6 C2s. So, and this plane of symmetry are going like this, you mean, right? That is what we
Yes.
wrote also, right? So one is here, one is here, one is here, and in between bonds also, one here, one here. So there are 6 sigma B's also. That is what we mentioned, right? Sigma B, 6. I have already mentioned that. One is plane of symmetry on the plane, that is sigma H. Okay. Plus there are 6 sigma V, which are like this. And when we will comment on the V or H, we will not consider this C2 anymore, because C2 is not the principal axis. Everything will be determined by C6, whether, but in this case, this is all the sigmas. This sigma, which is perpendicular to the board, is containing C6. So that's why it's becoming sigma V. Okay.
Okay, so principal axis is considered as C6 here.
Yes, yes, definitely. With highest n value, when there are multiple CNs,
Okay, okay.
the axis
Yeah,
with
got it now.
highest n value will be considered as principal axis. Yeah.
Okay, now got it.
Yeah. Okay. Next is point of symmetry. That's I or Ci. So in this particular case, what you have to do, you have to find out a point, one imaginary point, from where if you travel a certain distance, and find a molecule, suppose, or atom or group, whatever, from that point, if you travel or just measure the distance between that point, a certain atom, you have to go opposite direction, exactly same distance. You will find another identical atom or group. Then only you will say this point is the plane of the point of symmetry within the molecule. Let me explain with an example. Same molecule. Trans 1,2-dichloroethene. As I said, you have to find out a point here. Okay. And from that point, you will measure the distance of a certain atom, whatever. So we measure the distance of this chlorine, whatever distance. And after measuring that, what we'll do, exactly same distance will travel in the back side, in the opposite side. If you find the exactly identical atom, then we'll say this molecule having one point of symmetry. And the condition is you don't, or it's not only should be applicable between two atoms, all the atoms or groups of the molecule should be fulfill that feature, that opposite direction feature. All the should maintain that. So what I mean, we just mentioned about chlorine, but it should be from this point. Other atoms, the hydrogen in this case, also should be of exactly opposite side and identical distance. So this molecule is having only apart, and carbon also 6 atoms. Okay. Carbon is there. So you can see from this atom, doesn't matter which atom you choose, you go there and measure the distance, and exactly opposite direction you go the other side. So exactly same distance, you will get the identical atom. Okay. So that means.
Yes, so here even there is a 2 point of symmetry or only one? Because
Your voice is not very much. Can you please repeat?
sir, I was saying that so here are we having 2 point of symmetry or one? Because for one
No,
point,
only one. Only point of symmetry is only one always. There is only one point.
sir, so if
It's-
if such cases arise where suppose these two chlorine matches, but there these two hydrogen. So instead of one hydrogen, there is some other atom. So in that
then
case,
it will not be having no. Then it's not. It's not. Okay.
okay.
So like sigma or Cn, those are having multiple, right? So one molecule can have several sigma, several Cn, but this is unique here. One molecule can have only one I. Okay. So I is very unique. Only one I, and from that point, each atom, each and every atom should be. If you go there in the opposite direction, same atom. Okay, that should be applicable. Okay? All right.
Sir, can this point be along, and can this point be on any atom?
Yes, that can also possible. That point can be on an atom also. Yes.
Okay,
Yes.
sir.
So what he said that this point, suppose if you just replace hydrogen with maybe bromine, then there will be no I. Okay? So each and every atom should be there. What about the cis one? You see, is this molecule having any I here? If you consider individually, yes. If you consider individually, you can find for chlorines, you can find a point here. Then from here, you come here, you get chlorine. This side goes, same chlorine. For hydrogen, Okay, I got a point here. Okay, but that is not allowed. That should be a single common point from where each and every atom will get opposite direction met, same atom, opposite direction, same atom. That's why this is here, but in this case it's cross. There is no I there, no point of symmetry in cis-1,2 dichloroethene. But in trans, yes, it's having. All right. And not necessarily here. Also, the molecule needs to be planar. We can have non-planar molecule. So let us draw some other projections. We are only dealing with mostly Fisher and Sawhorse, flying wings. Let's put chlorine. We hydrogen. Okay. Is this molecule having any I?
Yes, sir.
Good.
Exactly at the center.
Yes.
Sir, but then this bromine one, can we connect it if we place the point in the center?
Your voice, there is a background noise. Can you please repeat?
Are you saying that if we place the point in the middle, so can we connect these two bromines?
Yeah, that's why that's good. I know from this drawing it's a little bit difficult to visualize. Okay. Here also please consider red as chlorine, okay? Chlorine here. Oops, no. This side, left side. From the mirror image. Let me exchange. Okay, we are ready now. Yeah. Okay. This is the situation here. Yeah. Can you see this? Let's check the pen. For the chlorine is easy, right? To visualize, very easy. That this is chlorine here. Okay. And yeah, maybe like this, better. It's chlorine coming downwards and this is going upwards. The point is here in between here. Okay. From here you can see from this point, you can easily apart from each other with equal distance going through the point. Okay. And in this particular case, bromine is coming this side, right hand side, and through hydrogen, left hand side. Or bromine is going towards you, hydrogen away from you. Towards you, hydrogen away from you. This guy is there. And in this particular case, this bottom, bromine is away from you, and hydrogen is towards you. Okay. Now from there, he asked whether this bromine, if you connect these two bromine with an axis, whether it will come through that point. No, it's actually here. You see, bromines are here. Yeah? Isn't it? Isn't it connecting and going through the middle of the carbon-carbon bond? Can you see this? See? This is a situation here. Same for the hydrogens. If you connect these two hydrogen, it's again going through carbon-carbon bond. Okay, this is middle point here. I hope from the model it's easily visible. Okay. Again, for the bromine, it's like this. Okay. It's going through the carbon-carbon bond. Okay, got it? Yeah.
But means the molecule can rotate and then the symmetry won't be there. So
Yes.
for
That's
any point, if it is there, then we say it is symmetric. Or
exactly. Very good
is
question.
this the stable condition? That's what we're saying.
No. Any point you have to any point. Okay. The answer is any point. Doesn't matter where's the energy. But any point, if the molecule is having that whatever sigma or Ci, then you can consider that. Okay? Unless it's mentioned that in the staggered form or in the eclipse form. So suppose this is the molecule, and then I asked you whether this molecule, I've given this molecule, okay? And then I've asked you to whether this is chiral or not. You consider and comment on this. And you just draw this molecule and then check whether okay this particular conformation is having I, so that molecule becomes, doesn't matter in which conformation, if some molecule is having I or sigma or Sn, then automatically it will become achiral. Okay.
Yes, sir.
Yes. Okay. So unfortunately we have only 1 minute. So what I'll do, I will skip that. Maybe I will continue next class 10-15 minutes on symmetry elements, because Sn is left, which is basically the most important, the alternating axis of symmetry. That is called the universal symmetry element. Although we have learned all this Cn, sigma, I, of course that is important, but if you learn Sn, and Sn is that's the most important, and we will see that Sn can fulfill the criteria of sigma, fulfill the criteria of I, and also it's plus some additional features are there. So that's why it's called universal symmetry element, Sn, so which is important to learn. In next class, first part, we'll discuss that, and then we'll change the topic and discuss the aromaticity part.
Sir,
Yes.
sir, I don't know if I'm right or wrong, but the diagram that were drawn for the chlorine, hydrogen, bromine, that one in the left hand side. No, sir, left hand side.
Okay.
No, sir, the board, that dashed line that we have divided the board, whole board. Sir, far left, yeah.
All right. This guy. Yeah. Okay.
Yeah.
Okay.
So
Yes.
here,
Yes.
this one means the front portion is correct, but so that is away from us, means that bromine.
Now,
So
this bromine is coming towards you.
yes, sir, that I got. Sir, I am just asking. Yes, yes. That second bromine, can
Yes.
we now draw that bromine from that from the point connecting hydrogen and chlorine towards the right hand side? That bromine that we have drawn under, can we now draw that to the right to the left hand side? I mean, first bromine you have drawn towards right hand side,
Yes.
and I am saying that the second bromine to draw towards the left hand side, as we have drawn it under that line connecting. Yes, yes, that bromine I am saying to just no, sir, from center to west side. I am just saying.
So let me show the model. No, is it visible from this
Yes, sir.
distance?
Yes,
This
sir.
model?
Yes, sir.
So this is the situation here. So this is the front carbon. This is the back carbon. Okay. Front carbon, chlorine is coming downwards. Bromine is towards you. You see, bromine is towards you. Okay. So you mean this guy should I draw here? That is what you mean.
No, sir. I am saying that the first bromine is okay, but
Okay.
the
Second
second
one.
bromine that is
Ah.
away from us,
Yes.
that I am saying that why are we not keeping it away from us?
This is away from you. No. This is like this. You see, the situation is like this.
Uh, okay, first, sir, is the first bromine away from us?
The first bromine is
According,
towards you. First bromine
yeah.
is towards you.
Oh yes, that's the okay.
First bromine is towards you, like this. No. Situation is
Sir,
like this.
I will mail you, sir. The diagram that I am trying to say, I will mail you. I can't explain it in words. So will that
No,
be
you
fine?
see, let me give you. So these are on plane, right?
Yes, yes,
Chlorine,
yes.
carbon, carbon, chlorine. These are on plane. Okay. And there are two V's. Two V are there, right? That like two horns of a cow. So there are two V's. One is, there are two V's. One is like this. You see, this one V. This is one V. This V is there. Okay. This V with the bromine towards you, hydrogen away from you. Okay. In this case, and in the other case, this V is going downwards like this. Okay. So hydrogen towards you, bromine away from you. And now how to draw this? This V is like this, no? But you are drawing the 3D thing in 2D. So anything coming this side means, in sawhorse, anything this side means towards you. This guy is towards you, this guy is towards you. Okay. Anything that side means on a particular carbon, I mean. Okay, with respect to this is back side, this is front side. You got my point?
Yes, sir. Yes, sir. I got that.
Yes, yes. Okay. All right, guys, then I will close.